Hello everyone and welcome to Stelzer Science. Today is a special lesson. We are going to be going over how to analyze graphs when it comes to AP Physics 1. AP Physics 1 is a course that really emphasizes graphing, whether that be analyzing graphs given to you or whether that be making your own graph. Now in this lesson we're mainly going to go over tips on when you see a graph on a multiple choice problem or an FRQ. What information can you get from that graph and how can you read that graph effectively in order to do the problem in question. So this lesson is not really fitting into one unit per se. It does use informations from unit 1, 2, and 3. So I'm requiring on you getting through kinematics, forces, and energy in order to understand everything in this unit. Because we're going to be looking at examples from graphs from those 3 units. So without further ado, let's go ahead and get into it. Let me minimize myself here. That's good. I think that's good. And let's get into it. Okay, so when you get a graph in AP Physics 1, there are many things that graph can tell you. From here on out, whenever you get a graph, there are 3 questions that you should ask yourself. 3 things to consider. Thing number 1 is, what does the curve tell me? This one's the easiest one. This one is just looking at the axes, and if the question needs you to get one of the axes, let's say you're given a graph of, let's say, force versus time, and you need to get a force at a specific time, well, their graph can quite obviously do that. It's giving you force, and you're just reading the axes. Thing number 2 is, what does the slope of the curve tell me? What do you get when you take the slope of the curve of the graph? Slope is rise over run. The rise is the y-axis, the run is the x-axis. So you're looking at the y-axis over the x-axis. If you divide the y-axis by the x-axis, what does that get you? Does it get you anything? And lastly, the third one is, what does the area under the curve tell me? To get the area under the curve, you are going to be multiplying the 2 axes. So area is going to be x-axis times your y-axis. If you multiply the 2 axes together, does that get you something? Does that lead to a new variable? So these 3 questions are the 3 questions that should be in your mind whenever you analyze a graph. What does the curve itself tell me? What does the slope of the curve tell me? And what does the area under the curve tell me? We're going to look at a few examples now. And the first example we're going to look at is a classic one. It's something we've already done this for, and that's, let's say, a velocity versus time graph. So in a velocity versus time graph, we're graphing velocity on the y-axis and time on the x-axis. So let's run through these 3 questions. What does the curve tell me? What does the slope of the curve tell me? And what does the area under the curve tell me? Starting with just the curve itself, we can get velocity and we can get time. So maybe a question's just asking when maybe we just need like the initial velocity. Well, the initial velocity is this x-axis isn't, the y-axis isn't labeled, but it's right there. That would be the initial velocity. And maybe that's all we need from the graph. Maybe we just need the initial velocity to plug into a velocity equation or a momentum equation. I don't know. But we can get velocity and we can get time. 2, what does the slope of the curve tell me? Now you can choose to analyze either the variables or the units. Let's look at the variables. So the slope, to get the slope, we're going to be taking velocity, which is the rise, over time, which is the run. Hey, velocity over time is acceleration. Your change in velocity over your change in time is acceleration. So what that means is you can get acceleration from this graph if you just look at the slope of this graph at any given point. So the acceleration from 0 to 1.5 looks like it's 0 because the slope is 0. Then the acceleration becomes a very big negative number. We have a very steep curve here, and then it starts to mellow out a little bit. So we can get acceleration. We can also look at this. Maybe you don't recognize the equation. If maybe you can recognize the units, however. So the units of velocity are meters over seconds. And then the units of time are seconds. Meters over seconds is meters per second squared. And that should be a unit that you recognize as acceleration. So we can get acceleration from a velocity versus time graph. Last one, let's look at the area under the curve. What can the area under the curve tell us? So the area in the curve will be doing velocity times time. Hey, velocity times time, your velocity times time is just your displacement. You can get displacement or position by taking the area under the curve of velocity versus time graph. The units tell us this as well. Velocity is meters per second, times that by seconds, and we just get meters, the unit of position. So if we take the area under this curve, that area, we can get the displacement of whatever this object is being graphed. So there are 4 things that we can get from this graph. We can get acceleration, we can get displacement, we can get velocity, and we can get time. A question can give you a velocity versus time graph and expect you to get any one of these 4 things. So you need to know how to get any one of those 4 things. And part of it is, are you familiar with all the equations in this class? You're given an equation sheet, so hopefully you can make yourself familiar during the test. Let's look at another example. Let's look at this acceleration versus mass graph. We're graphing acceleration versus mass. So first one, question 1, what does this graph actually tell us? Well, obviously we can get acceleration and we can get mass as part of this graph. Maybe we just want to know what the acceleration when the mass is 10. So go to 10, go up. What's that acceleration? Maybe like 0.85 it looks like. That can be something you have to do. Not too hard. 2, what does the slope of the curve give us? So the slope of the curve is going to be acceleration over mass. Does the slope of this graph tell us anything? I don't really recognize anything from acceleration over mass. Meters over seconds squared over kilograms are the units. That looks like a big nothing burger. We don't have an equation that does acceleration over mass. Not saying that every single graph or every single slope will tell you something or every single area under the curve will tell you something, but you do need to identify when it will tell you something. Let's look at the area under the curve. If we do the area under the curve, we're going to be doing acceleration times mass. Acceleration times mass, this is the biggest equation in Physics 1, is force. Force is mass times acceleration. F equals ma. What that means is if we take the area under this curve, this area, we will be getting a force because just mathematically, a force is an acceleration times a mass, or a kilogram times a meter over second squared, which is the unit of newtons. So if you were given this graph of acceleration versus mass, you would be expected to know how to get force from it. It's not too hard. You just have to recognize that if we multiply the 2 axes together, we get force because one axis is acceleration, one axis is mass. Acceleration times mass, or mass times acceleration, is force. And then we move on. You find that area under the curve, and then you use that force in one way or another. Let's do one more example here before we actually jump into a problem. Energy versus time. So again, let's just run through the three things. What does the graph tell me? We can get energy and we can get time from this graph. Maybe we want to know what the final energy is. Maybe we want to know at what time is the energy 20 joules. I don't know. There's no question associated with this, so we're casting the wide net and seeing what this graph could give us. 2, what does the slope of this graph give us? If we take energy over time, which is the rise over the run, energy over time, or change in energy over time, is power. Change in energy is also work. So we can get power by taking the slope of this graph if we're looking at the change in energy versus change in time. The units, maybe we can identify this from the units. Power, or the units, are joules over seconds. Joules over second is the unit of power. So if you're given an energy versus time graph, you can get the power by taking the slope of the graph. A question would expect you to know how to do that just looking at these axes. Last one, what does the area under the curve tell us? To get the area under the curve, it's going to be energy times time. So energy times time. Or unit-wise, joules times seconds. This one's a really, really tough one to see, but the joules times seconds is actually the unit of angular momentum. It matches up with the unit of angular momentum. That's a little too difficult to see, especially since we haven't learned angular momentum at the time of recording this video. I've never really seen that one come into play, but it's technically one that does match up. I think the big one with this one is, can you get that power is joules over seconds, is energy, change in energy over change in time? Now, a question is going to give you sort of hints on how to analyze a graph. It's never just going to give you a graph in isolation like I just did with the past 3 examples and say, and ask you to do something. You're going to kind of have an idea of what you need to get. Rather than explain that more, let's just jump into an example. So this is the only example I really have. Let's read this example. A force is exerted on a block as the block slides across a horizontal surface. The graph shows the magnitude of the force as a function of the block's position. So we have force and position, force and displacement. What is the total amount of work done on the block by the force during the interval shown in the graph? If the block starts from rest, what is its velocity after 1.5 meters if its mass is 5 kilograms? So here we have a graph of force versus displacement. And this is what I mean by the question will give you some guidance on what to do. We're trying to find work. We know that work is force times displacement, and we're graphing force versus displacement. So what that lets us know is that the area under this curve, because to get the area under the curve we're multiplying the axes, will give us the work, and that's what the first part of this question is asking us to do. How do we get the work? So let's go ahead and do that. We need to get the area under this curve to get the work done. What is the total amount of work done on the block by the force during the interval shown on the graph? So to get the area under this curve, let's take this in 2 parts. Let's take the area under this triangle and add it to the area of the rectangle underneath the triangle to get the total area. So the triangle length, or it's 1/2 times base, which is 1.5, times height, which is 5. That is 3.75. And the red area, it's just 5 or 1.5 for the length. The height is 5, which is 7.5. Add those two together, 3.75 plus 7.50, and we get 11.25. And that is the area of the curve, so that is the work done. Simple as that. But the question, the hard part is, can you see that from looking at the axes? Do you know that you can do that? Do you know that you can multiply force times displacement and get work? And do you know that means taking the area under the curve? Second part, if the block starts from rest, what is its velocity at 1.5 meters if its mass is 5 kilograms? So to analyze this question, we're going to use the work energy theorem. Work is equal to the change in energy. There's no potential energy as a part of this problem, so it's just going to be the change in kinetic energy. The work is 11.25. We just found that, and that equals the final kinetic energy. So 1/2 mv final squared minus the initial kinetic energy, 1/2 mv initial squared. Magnitude of force, what is the total amount of work done? The block does start from rest, which means the initial velocity is 0, so the initial kinetic energy is 0, so 11.25 is going to equal 1/2, the mass is 5. We're solving for the final velocity, and if we put that in our calculator, we get a final velocity equal to 2.12 meters over seconds. Work energy theorem question there. All right, to finish this off, so analyzing this graph, we can get force, we can get displacement. We talked about that we can multiply force times displacement for the area under the curve to get work. Is there anything we do with the area under the curve? Just for fun, let's just see. Or not the area under the curve, but with the slope. For the slope, if we take force over displacement, unit-wise, that's going to be newtons over meters. This is a pretty tough one to see, but that is the unit of spring constant, newtons over meters. Another place we often see force versus displacement graphs is analyzing springs. I've seen a lot of questions centered around a student is doing an experiment with a spring and they're graphing the force versus the mass, or their force versus the displacement of the spring. So they're stretching the spring out to different intervals and graphing the force. Well, in the context of that question, it's going to be easier to identify this. However, if you're given a force versus displacement graph in a question like that, you should be able to recognize that if you take force and divide that by displacement, that is the units of spring constant, so therefore the slope of that graph gives you spring constant. So that goes back to what I said about the question will kind of guide you into what to do. You wouldn't necessarily be looking for spring constant in a question like this because there's nothing about springs in this question. But in a question with an experiment about spring, you'd be more alert to that and more ready to see that. But again, this whole lesson was simply just about, can you take a graph and look at it 3 different ways? Can you look at it in a way that, let me go back to full screen. Can you look at it in a way that looks at just the axes? Can you look at it in a way that looks at the slope? Take the y-axis over the x-axis, what does that give you? And finally, can you look at it in terms of area under the curve? If you take the y-axis and multiply the x-axis, what does that get you? AP Physics loves these questions. They love giving you a graph and having you analyze the graph. I see it all the time. It's not too difficult, but it requires familiarity on how to analyze graphs and in terms of the equations themselves. Use your equation sheet. The equation sheet is so good at just plotting everything for you. All right, that is where we're going to end this lecture. I hope this helped. I hope this is going to help us with graphing moving forward. But that is all that I have for this lesson. Have a good one, y'all, and I will see you back in the classroom.